Okay, thank you, Marie, and thank you, Eigen, for inviting us to your user forum. I'm going to take you through the agenda. So my name is Gjermund Weiss. I'm COO of Turbulent Flux. We will do the introduction of what is really virtual flow metering and some use cases of virtual flow metering. Then from Visualising Data, Marianne Rolland will talk about virtual flow metering use case. We're working together with both Eigen and Visualising Data. And then Murray will see how this looks in Eigen Ingenuity. And then on my right-hand side here, Sigurd, my colleague, will go through how we keep the virtual flow meter accurate. First, about our company. If you don't know it, we're about 20 people located in Oslo, coming from the multi-phase flow simulator community in Norway. We have developed a completely new technology stack for transient multi-phase flow simulations that is targeted for operations and really the digital transformation, scalable and easy available. So basically giving you information about the flow in wells and pipelines, looking at flow rates that we're going to look at now, obviously, with virtual flow metering, but also pressure, temperature, other slugging, hydrate wax, these kind of flow assurance related issues we also work with. We have validated our technology with several operators globally. These are three that we have selected that we are working with now, just to show you who some of them we are working with. So our technology works in the cloud. It's a native cloud software subscribing on the sensors from the operational system and calculating let's say all the features from the flow. And this is, of course, oil, gas, water rates when it comes to these virtual flow meters that we are sending back to typically an operational database that can be visualized in tools like Eigen Ingenuity. So virtual flow metering, just if it's new for some of you probably, it is, as I say, calculating the phase flows coming out of the well. We, as we have a flow simulator, we do a physical description of your system. There are different types of systems. Here you have two, gas lifted and then the ESP driven systems. And then we typically subscribe to different types of sensors, pressure, temperature, downhole at the surface. What is the production choke setting? There can also be some sensors that are missing. Then we might also end up doing soft sensing with the machine learning to replace the missing sensor that we are using in our multi-phase flow simulator when we do the calculations. So here is a user example, a very typical user example, why you want virtual flow metering. So you are getting flow rates from the phases in real time, 24/7. The value of that is, of course, to monitor your flow. And also see that your flow is according to what you expect from the production. And also, obviously, to see if there's not performing, what is happening, and you get an early detection of something is wrong, so you can select the wells that you want to look more closer into. That's a different process. So it's really about digitalization of this is kind of a cash register every well you have, and also to minimize the human intervention of checking wells frequently, doing a lot of well testing, costly things, so you can reduce these things, but you're actually better informed. So you can be more proactive than reactive. Here is use cases, just say it varies from field to field and assets to assets. And here is a typically use case that we see on not so relevant for this forum, I think, but it's onshore in the US. We have every well is typically having one test separator to monitor and surveillance of each well, because they want to allocate the production And they also want to see if there are any upsets in production, so they can act. So they know when to drive the truck to the well pad and look at the well. So they want to keep this, obviously, this information, but then you can go over to virtual flow metering, where virtual flow metering is filling in where you are lacking separate testing. So here is an example that you reduce, for instance, you have several separate vessels, and you can reduce it like here for 1 separate vessels for 6 wells. And then you do intermittent testing, which is typically offshore, not so typically here onshore, but then you use the intermittent testing to validate and make sure your virtual flow metering are accurate as a poor performance as expected. So obviously you then save a lot on investment and operations of the separators when you can reduce the number of units. There's another use case where this virtual flow meter is giving you consists of a model of your whole well. So it also calculates the flowing bottom pressure on the sand face. So from between the reservoir contact between reservoir and the well. To have an accurate approach for this, a soft sensing on this can be very valuable for reservoir engineers because they are putting this into the reservoir simulations, what is going out of the wells, so they can improve the reservoir simulations. And then you can also improve your strategy of how you drain your assets, which obviously has a potentially high value on increased overall production. So I think that was the use case I want to mention. So now I leave the word over to Marianne Rolland from Wintershall Dea, who's going to talk about the virtual flow meter use case they are working on.
Thanks, Jan. So the challenge we in Wintershall Dea is focusing on is how can we best distribute the gas lift we have available on our wells to maximize the production. The setup now is we have a test separator where we route the wells to, and so the optimizing points are scarce and far between. So if we get the reliable real-time data for the virtual flow meter, we can be more confident that the changes we do to the gas lift distribution will have a positive effect on the overall production. And also it will save us time making those kinds of decisions, and also time spent on the daily allocation of production well by well. So to help us visualize this and evaluate the performance of the BFM, we have gotten then Eigen into the loop, and then Murray can talk more about the details on that, but that is giving us a great tool to look into how is the virtual flow meters performing relative to the well test we are doing. So on the well test, we might change the gas lift settings and see that the VFMs can catch the changes we actually see on the production, now the test separator, I mean. So Murray, if you want to go into the details.
Yeah, thanks, Marianne. I'd actually like to invite one of our engineers, Ben Hickey, to talk a little bit about this. To give him credit, he's been doing all the hard work behind the scenes on this. So Ben, if you maybe just wanted to share your screen briefly, and you could show the, well, in fact, yeah, Ben, I mean, maybe why don't you just talk through the these slides briefly, and then just show, you can show the actual trends in real life.
So basically, it's a lot of data. We get our data from turbulent flux and windchill data into the analytics platform through CDF. We pull in all of that, the turbulent flux tags for virtual flow, and the flow rates from test separators and the like. But we also have well test data that's recorded manually in an Excel spreadsheet, which we've set up a script to pull in, which takes stuff like average well flow over a well test, start and end dates of well tests, and stuff like that, which is quite useful for some of the things this uses. For example, we need the start and end dates, which we store on our event scanner, in order to plot stuff specifically between the start and end date of a well test, as well tests have variable durations, which is not something we can adaptively do in Ingenuity, but using the event scanner, we can use that as triggers for our calculations. So if I share my screen, I can't share my screen while someone else is sharing, sorry.
Yes, you need to stop sharing at turbulent flux, please.
Oh,
There we go.
There we go. Yeah.
Sorry, 1 second. So I've got to update my security settings to let Zoom share my screen. Sorry. 1 second.
It's entirely possible that Ben's had to rejoin the meeting after changing his security settings.
Yeah, sorry, I had to
yeah,
restart it
right.
to let me share my screen.
Yeah.
Right, here we are. Okay, so for visualizing the data, we've created 2 pages specifically here. One driven off of this page here, I'm showing is driven by the asset model. It's in the dedicated turbulent flux space of this Ingenuity. Oh, sorry. And essentially this it uses our object template, which is driven by our knowledge graph in Neo4j, and it will plot the turbulent flux rates for oil, water, gas, and gas lift, all taken as a 90-minute average because the raw tag is quite noisy in comparison to the turbulent flux rate. But it will plot it over, you can either have it in live mode, or right now I've got it set up to be over a specific well test, just so I know what I'm looking at. But it plots, this is asset driven. It's the current well selected in the object template, the water rate. This one would be the oil rate, the gas lift rate. And this tag here is just the average from the spreadsheet I was talking about. Oh, sorry, no, this is from, this is the rate from the test separator averaged over 90 minutes. And these 4 graphs are all synced. So if I were to change this time, it would change for all of them. So you're comparing the same time window for the 4 values. And you can quickly change between wells. So that was AO4, this is AO7. Obviously, we were looking at a time when AO4 was on test, so the test separator hasn't changed. So obviously this is not a useful comparison until you change to the well test for the well you're on, but it's very quick to change between well, and then if you have ready the time of a well test, you can quickly switch to it. It's very good for that. Then let's see, we've got, my other page is this one is just a, so this here you can see is, these are 2 different lengths. These are 2 well tests that happen pretty soon after each other. These are both for AO4. Using the Python script, we are detecting the start and end date of the wells. And so we're only plotting when the well is on test, because really there's no point in plotting the oil rate when against the test rate when the other well is on test. But here we're plotting the average from, I'll just make it a bit bigger. We're plotting the average over the full test against the current rate, and then we're plotting the cumulative rate over the same test. And as you can see, the water rate specifically are very accurate, which is the use case. But this is done through Python of, again, I say, looking at the knowledge graph looks at the wells for the other one, but this one is just for AO4. We've made this page. It will plot for the well test. This Python script I've made here pulls the data from the event store for the start and the end of the well test, and will totalize the calc for turbulent flux and from the test separator up until the end, then reset. So essentially you get an accurate comparison of the cumulative rate for each over the well test. And this is what we've done to help visualize.
And Ben, I wonder if you could just turn on the actual test separator flow.
Oh yeah, the reason we use the average is because the actual test separator flow is very noisy in comparison, and even giving averages, you have to get to an average quite like that would go off the edge of the well test in order to get it to be in a similar vein to the oil rate, which is why we decided to use the rate from the spreadsheet, which is the rate over the entirety of the well test. So this is just a flat value for the well test, whereas this is not very useful for comparison, we feel, which is why we decided to do it that way.
Yeah, I think that's a great just illustration of the realities of an actual meter, even when you have one. Actually, it's not necessarily a usable number, and so the real comparison was against the sort of post-process actual well test rate, and that was what the virtual flow meters had to are being matched against. So thanks, Ben. I think it's great to see just a simple comparison. Also, it's pretty quick now, which is great. So, but thanks, Ben. Sigurd or Geirmund, can we hand back to you to?
Yeah, so Sigurd is going to take us through how we keep the virtual flow meter accurate at all times.
Thank you, Edmund. So I'm going to talk a bit about how we are keeping the flux VFM accurate over time. So this is a timeline representing the flux VFM in operation. The transient multi-phase flow simulator calculates flow rates continuously with field pressure and temperature measurements as inputs. It also receives inputs from machine learning or analytics models. These inputs are typically water cuts and soft sensor values, for example, missing pressure measurements. The field conditions, as we know, are ever changing. And to ensure that the VFM stays accurate over time, we apply the concepts of tuning, training, and self-adjustment. So when the well test has been done, the well test rates are compared with the VFM rates. And if required, the machine learning models are retrained, the simulation model physics is retuned after the well test. And between these updates, the VFM is completely self-sufficient, and the self-adjustment concept is key in this. So self-adjustment, the Flux VFM includes a reservoir inflow model, and it applies a combination of machine learning, numerical optimization methods, and flow simulation to calculate inputs for this reservoir inflow model. And these inputs are the reservoir pressure, temperature, the gas-oil ratio, and the water cuts. The calculations are fully automated, and they are performed typically 1 to 4 times per day. And this way, the VFM stays accurate over time with a very limited human intervention. So please reach out if you have any questions or queries regarding the Flux VFM. Thank you very much.
Thank you, Geirmund and Sigurd. I have one question with the auto learning, the retraining. How do you make sure that the conditions for a retraining are valid and it's not something induced externally, like they've shut in the well or something, or choked it down and so the bottom hole pressure is increasing? Is there like a a flow scheme that validates when something's changed in the reservoir versus externally?
So of course, at this point, a data scientist has to review the data before retraining the machine learning models. But we are working to automate this process to a higher and higher degree. But for now, of course, there are a few manual steps involved in this process.
So another thing is also that we also filtering the data before we use it. So if there are any bogus data coming in, we will filter them out. So there's a logic there as well. We don't use the raw data as is.
Yeah, okay.
No, I have a question as well. If you could go to the previous slide, Sigurd. So here for the reservoir, you have the pressure, temperature. I mean, these things don't get measured all the time. Do you assume they are static for a period, or how do you update those?
So they are updated by the optimization or the machine learning models. So a typical case is that we have a machine learning model updating the water cut on an hourly basis, and then we run numerical optimization to estimate reservoir pressure, temperature, and gas oil ratio, typically 1 to 4 times per day.
Got it. So you basically you run a numerical method to find what the best fit for those values would be to match the data.
Exactly. So we match the field measurements. So we match the downhole pressure, the wellhead pressure, and using the field measurements basically. So then the downstream choke pressure, the choke position are inputs, and then we match the wellhead pressure and downhole pressure using numerical optimization, and we arrive at the reservoir pressure, temperature, and gas oil ratio.
Right.
Also out there in practical life, it's not like you have sensors everywhere, and typically downhole sensors over time they fall out, they burn out, and then we are using transfer learning from other wells to make a soft sensor out of that with machine learning that our simulator can use as a matching parameter. So you're not if you lose your downhole sensor, you're not kind of losing your virtual Flowmeter.
Okay.
Yeah.
Thank you.
Yeah, thank you. I think one of the things worth highlighting is that this was a really good collaboration, because you read data out of the Vintage data hub, right, to get your, say, sensor data. Then you do your virtual Flowmeter calculations, and then you write that back into like the value add, and then it comes back into a single place. And Marianne, I don't know if you wanted to comment on anything about that, but it was my understanding from, say, Peter, was that this was a great example of how your digital platforms now are enabling these collaborations to start happening, and plugging in these advanced features from outside and bringing them in to expand stuff. I think as opposed to, say, the Turbulent Flux having to set up its own sensors and get its own data feeds, you were able to just come in and deliver the value that you had.